Welcome. This is our second lecture on a Greene-Kleitman theory, and we are going to follow work of Viennot, who introduced a new view on Greene-Kleitman topics for two-dimensional orders. So this will be a quite colorful lecture with many nice pictures, but we start with something classical. We start with something that comes from representation theory. It is Young Tableaux. So to define the notion of a Young tableau, we need the notion of a partition. So a partition of a number n is some lambda, and this lambda consists of a vector sorted entries lambda mu, and the point is that the sum of these lambda i's from 1 to mu is equal to n. And so we denote this as partition lambda of n. And well, here's an example. We can take the vector 5, 2, 1, 1, and this, if this is lambda, then this is a partition of 9. And there's a very nice way of visualizing partitions. This is given by the Ferrous diagram. F of lambda, and for the Ferrous diagram, we take the entries of the partition and we take a pile of cells of the given height. So we start with a pile of 5 cells, then we add one with 2, one with 1, and another one with 1. This would be the Ferrous diagram of this partition. Okay, and now given the notion of partition and the notion of Ferrous diagram, we can talk about Young tableau. So Young tableau of shape lambda is a filling of the cells of the Ferrous diagram of lambda with numbers 1 to n. Here we assume, of course, that lambda is a partition of n. And this filling has two properties. It is, well, every number occurs, so it's a bijection between the cells and the numbers, and it's monotone in rows and columns. So it's increasing in rows to the right and increasing in columns upwards. So an example is 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be a Young tableau of this shape. Yeah, and now there is a famous result associated with the names of Robinson and Schenstedt. Schenstedt correspondence. It comes from representation theory as a notion of Young tableau, and it says that there is a bijection between permutations and pairs PQ. So this pi is a permutation in the symmetric group on n elements, and PQ is a pair of Young tableaux of the same shape, lambda, which is a partition of n. So pairs of Young tableaux of shape of size n and the same shape lambda correspond bijectively to permutations. And well, if you have this theorem, and if you denote f lambda to be the number of Young tableaux of shape lambda, then the theorem tells us that we have the following beautiful formula: n factorial is equal, this is the number of permutations, and on the other side we take a summation over all lambda, with lambda is a partition of n, and we take the f lambda and we square it. So this is a beautiful identity. And yeah, let me comment on the, so far we don't see a connection, but in the first paper on Greene-Kleitman theorem, a paper by Greene from the early 70s, the paper is called on how is it called? Extensions of Schoenstedt's theorem. So this is Schoenstedt, and Schoenstedt showed that if you have a permutation and you have these shapes, then row and column lengths of this shape correspond to the longest increasing, respectively decreasing sequence in the corresponding permutations. And Greene generalized on this. Yeah, so let me briefly tell you how this theorem is typically proved. The typical proof, which goes back to Schoenstedt, is via the bumping algorithm. So the bumping algorithm is taking a permutation and it generates the two Young tableaux associated to it. So we have pi. I'm giving a very brief description of the algorithm, and then we look at an example. So the idea is that you go through pi from left to right, and what we do is we take the element that we have in the end, and in P column by column we insert x, or we bump the minimal element y, which is larger than x, and push it to the next, and go with this element to the next column. So this is if you have seen the example, you will understand the description. So let's just go for an example. Here is permutation pi, copied from my sheet. 1, 3, 6, 8, 4, 9, 2. So we have two things we can do with our element. We can either insert or we can bump. So now let's start from left to right. The first thing is we go in the first column and we put the 7. Now and we are going to build a young tableau. So we are going to build something which is monotone in increasing upwards in the column and increasing in the rows. So now we come with a 5, and we cannot put 5 above, we cannot insert, so we have to bump the 7. We bump the 7 and we replace it by the 5, and then we go to the next column and there we can insert the 7. So we have a bump step and an insert. First one was a bump and the second was an insert. And now we come with a 1 and it cannot go here, so it has to bump and we get the 1 here. Now we come with a 5 and we cannot put it above the 7, so we have to bump again and we insert the 7 in a new column. So we have 2 bumps and 1 insert. Now we come with a 3. And well, this time we can put the 3 right on top of the 1. 1, 3, 5, 7, and this was just a single insert. Now we come with a 6, and again we can put the 6 on top of the 3, and we have a single bump insert to get to the next one. And now the 8, and again same thing, we can simply put it on top. 8, 6, 3, 1, 5, and 7. And now we come with the 4. We cannot put the 4 on top of the 8, so we go down in this column to find the element which we can bump out. And so the first element, which is at least as large as our 4, is the 6. So we bump out the 6, and we can put the 6 on top of the 5. So the next thing will be, here we have the pile 1, 3, 4, 8, and here we have the bump, the 5, 6, and the 7 is here. So this was obtained by 1 bump and 1 insert. And now we come with the 9, and we can put the 9 on top. So it's just an insert, and we have 9, 8, 4, 3, 1, 6, 5, and 7. So finally we come with the 2. And the 2 is going to bump something from the first column, the first element, which is larger. So it's going to bump here. Then we go in the second column with the 3, and the 3 is going to bump the 5 out. Now we go with the 5 in the third column, and it's going to bump the 7 out. And finally we put the 7 in the new column. So this will be a sequence of 3 bumps and 1 insert, and the picture, and this is our final tableau. So here we have the 7, the 5, 1, 2, 4, 8, 9, the 6 was staying, and here we put the 3. So this is the final result of our bumping algorithm, and this is the P symbol, the P from the bijection, the first entry. And now what is the Q? The Q is the gross young tableau. P. So we get the very same shape. And now we put in each cell the moment when it arrived. So this was of course the first cell that arrived, and then we had this one, and we went here, and here, and here, and now we got the corner cell, and the top element here, and this is the, so this would be the cube. And this is the bumping algorithm for this explained on this permutation. And yeah, by analyzing this algorithm, you can come up with a proof of this theorem. But we are going to look at it differently. So we are going to take the permutation, and with the permutation we have a two-dimensional poset. So the poset, which has a realizer, identity, and pi, is a two-dimensional poset, and actually this realizer is already allowing us to draw the poset as a set of points in the plane. And I have prepared this for you, so let's have a look. Here we have the two-dimensional picture. So here we have the identity 1 to 9, and reading upwards here, this should be the same permutation that we have over there. This would be a picture of the poset. With X, we denote the ground set. Okay, and now what we do is we work on this drawing, and we are going to build the canonical anti-chain partition. So the first anti-chain would be the minima, but we are going to construct it geometrically. This is somehow related to the orthogonal surfaces that we have seen in the context of incidence orders of planar graphs. So the three minima are these, and the corresponding orthogonal surface in 2 dimensions is this object here. And we are going to call it a jump line. So we build a jump line on the minima, remove them, and iterate. So this would be the second anti-chain in the canonical anti-chain partition. And we continue. Okay, so this is the canonical anti-chain partition built by jump lines. And now these zigzag lines, every lower corner has a point of X. But there are these other corners. We have these corners. And well, these corners are the skeleton points of X. So we get S of X is skeleton points. Now we have a new set of points in the plane. And what we can do is we can change the color, and we can do the same thing with our yellow points. We can build the canonical anti-chain partition by drawing the jump lines. So the jump line here would be the first jump line, and then we have a second jump line. And that's it. And so this would be the S of x, also S square of x. And, well, yeah, so these are the jump lines, and now, again, the lower corners are already occupied, and this object that I already announced is the set of upper corner points. Just these two. Okay, and next color, we take the canonical anti-chain partition by jump lines. This is very easy in this case, and we get yet another point. So this is now the point which is, yeah, the set is the third power of the skeleton operation, and now finally we have only one jump line and an empty skeleton. Okay, so now let's see what we got here. I'm going to. This is a bit large. I need a little bit of space. So let's say we understood this. So what we are going to do now is we look at the right outgoing lines. Right outgoing. And on the right outgoing, we see 5 yellow outgoing lines. And the heights are 1, 4, 5, 6, and 8. And then we see 2 red outgoing, and the heights are 2 and 7. And then we see 1 blue at height 8, and 1 green at height 9. Well, and we can do the symmetric thing. We can look at the top outgoing lines, and what do we see at the top? So again, we see 5 yellow, and they are at position 1, 2, 4, 8, 9. 1, 2, 4, 8, 9. We have the 2 red, and they are at position 3 and 6. And we have 1 blue at 5, and 1 green at 7. Okay, and now let's have a look on the other side. So the P symbol here is recognized to be the top tableau that we got from this picture. And this tableau is on the something wrong here. What's wrong? Oh, so this Here I was wrong. I don't know what I did. This is 2 and 7. 2 and 7. Where did I? No, should be the 2 and 7, but this is wrong. This should be a 3. This was okay. 3, 6, and 5. And so this should be the top. So this is a 7. 1, 3, 5, 7. Yes. 2, 6, 4, 8, 9. This is the P symbol, and now let's compare it again. Having replaced the blue entry, we have the Q symbol here. So with this geometric thing, we seem to produce the very same Young tableaux that come up from the classical bumping algorithm. And yeah, so now let's see. Let's see what we plan for today's lecture. We have we want to prove 3 things. So the first thing we want to prove is that we get the bijection pi with P and Q. And we're going to base the proof on this construction. And now the interesting thing, which is connecting us to the Greene-Kleitman theorem, is that the shape of our P and Q symbol is precisely the shape that we associate with the poset P of pi. So the height of the first pile is the height of the poset. The height of the first 3 is the 3 height, is a maximum size of a 3 chain in this poset. And dually, if we take the first the longest L columns, then we get the size of the maximum ell-antichain. And this is what we prove in 2 and 3. So 2 will be constructive proof of WL. So this is a maximum size of an ell-antichain, and this is equal to the number of cells in the L longest columns of, let's say, of lambda. And the third one will be constructive proof of the dual statement that HK is equal to the number of cells in K longest sorry. This was rows. We are going wide, and here we go high. So this is the columns of lambda. Yeah, and one thing I should remark at some point is that well, for drawings of Young tableaux, there are different conventions. So many people draw young tableaus in this form. So this is sometimes called the French way of doing the Ferris diagram and the young tableaus, and this is the American one. Also, the typical description of the bumping algorithm would go row by row. So you try to insert in a row, and then you go to the next row. So there's a certain, yeah, things are done differently. Be careful if you look at it. Okay, so this is what we plan to do. And now, before we enter the proof, let us mention some consequences. So, one thing which is immediate from this description of the tableaus associated to a permutation is that, well, if you reflect the picture at the diagonal, then you exchange the P and the Q symbol. You exchange the outgoing lines on the right and the outgoing lines on the top. But in terms of the permutation, what you're doing is you're going from, you have to relabel things so that down here you have the identity. And then after reflection, you would have the inverse of pi here. So what we see is that if pi maps to PQ, then pi to the minus 1 maps to QP. As, of course, this is if and only if. And this is something which is obvious here, but if you go through the bumping process, this is completely non-trivial. Yeah. A second thing which is direct here is that the shape wait a second. Yeah, no. From points 2 and 3, imply what I said before. That's the shape of P equals the lambda of P pi of Greene-Kleitman. But this is something I already mentioned. In the Greene-Kleitman theorem, we associate Ferris diagram to every poset where we have exactly these two identities. And now a third thing is that for every pair KL on the boundary of the shape, we get an orthogonal pair CA, where C is a K-chain and A is an ell-antichain. Now, this requires a proof. Let's see proving something. Okay, so given CA, where we have two properties. So the first one is that the size of C is equal to K, so it's a K chain. And the number of elements covered by C, by the chains in C, is what we, some S, and we assume that it's at least as large as the number of cells in you're going for the C, so this is the columns. Cells in longest K columns. And for the A, we assume that it's L, so it's an ell-antichain. And this time it's a T, and it's at least as large as in the longest L rows. Now, from this, we let's have a look. Let's have a look at the diagram. So we have a K and an L, and so this diagram has n cells. And now we have the size of this S is at least as large as the number of cells here. The T is at least as large as this number of cells here. So we get that this N. And now the amount of stuff that will come twice is at most K times L. So if you think of the elements of P, then every chain and every antichain can have at most one element in common. So if we look at what we count twice by taking this plus this, it cannot be more than K plus L. So we get that the N is at most S plus T minus K. Okay, and now let's look at it differently. So N is at least as large as the stuff that is actually covered by the union of all elements in A and all elements in C. And now this is equal to S plus T minus the size of the intersection. But the intersection, this is something we already saw a moment ago. We can go over all antichains in the family and all chains in the family, and we take the intersection of A and C. And this is less equal 1, so in total this is less equal K times L. And yeah, so because it comes with a negative, we have this is at least S plus T minus K. So you see, we have n less equal, we have n increased as large. So we find n is equal to S plus T minus KL. And from this we conclude that we have equality here. So we have a, let's put it the way we wrote these things in the last lecture. So together the chains in C and the antichains in A are covering everything, all the elements of the poset. And the second property that we get from knowing that we have equality everywhere here is that we have equality everywhere here. So we have the size of A intersect C is equal to 1 for all A in A, C in C. And these two properties you can recognize. These are the two properties that we used to define orthogonal pair. So we get that C A is an orthogonal pair. Yeah. So we are going to exploit this statement that for every pair KL on the boundary of the shape, we get an orthogonal pair. So from this we get several things. We get L-saturated chain partitions. C plus. So the idea is you take the shape, you look at L, and then there is some point on the boundary. You get a corresponding K. You get a chain partition CK, so that CK with AL form an orthogonal pair. Now you add to the chain family of size K, you add the remaining elements as singletons, and what we saw last time is this is going to be an L-saturated chain partition. So this is going to prove theorem 1 or 2, one of the two from the Greene-Kleitman theorem. And dually, for all K, well, for every K we get a K saturated antichain partition. And we do the dual thing. So we start with K. We find some corresponding L, so that KL is on the boundary. We get the families, and this time we add the singletons to the antichain family. And also the transition, the T phenomenon. So the idea is, if you have this K and you look at the corresponding CK plus is saturated for all these values. Yeah, for all the L's in this interval. Let's do it symbolically. This is some interval I, and all the L's in I. This very same thing is orthogonal. So whenever you have two consecutive values, then you can find the edge on the other side. And this is at some k, and you get one K partition which is saturated for both values. And of course, the same thing can be done dually. So if you review the 5 theorems that we had in the context of the Greene-Kleitman theorem, all 5 theorems can be proven by proving what we have on the plan, by proving these two statements. Okay, so now we are going to enter the proof of these things. Of course, we start with 1, but actually before starting, we have a little lemma. Which is going to, it will be good to keep it in mind. We have a set of jump lines. So this simply means it's a set of objects of that kind. Yeah, the top and right outgoing and a zigzag in between, and then we have AI is a generating set of Ji. So if this is a jump line J, then the lower corners would be the generating set. Now, we define a set which is just the union of the AIs. And now we have two things which are equivalent. So the first one is that this family AI 1 to k is the canonical antichain partition of the underlying set. So need not be in the right order. The indices can be scrambled, but the antichains are the antichains of the canonical antichain partition. And the second property is something which is more geometric. The J is non-crossing. So it's a non-crossing set of jump lines, and well, if you go to our example, I mean, clearly we have this property that we have that the yellow jump lines are non-crossing the red ones, and so on. Okay, so what can we say to prove this? Well, so both directions of the proof can be done on an inductive way the amount of the size of k. So if we just have one jump line and one generating set, then it's obvious. And now the inductive step consists in removing the lowest antichain. So in this direction, so without loss of generality, it's the first, which is the min of y. So we have a given canonical antichain partition. And now this implies that everything else is above the jump line of A1. I mean, this is how we define comparabilities. Everything is, we have the A1, and every other element is comparable to one of them. So every other element is in the quadrant spanned by one of these elements. So it's above the jump line. And therefore, J1 is not crossing the other jump lines, because the other jump lines have to be spanned by this is bad. Have to be spanned by elements which are in this upper part. And yeah, the other direction, if we have such a non-crossing set of jump lines, then we see there exists a lowest one. And again, we are taking it to be J1. Well, and for all I not equal 1, the jump line Ji is above the jump line J1, and this implies by the very same argument that AI is larger than A1 in P. And yeah, so this implies that A1 is equal to min of P. And that's everything we have to do for the proof. Okay. So now let's get more serious about this, and I again start by getting some space. So the first thing we want to do is we want to show that, that indeed the two objects that we get here by taking the outgoing lines on the right and on the top, and these two things are indeed tableaus. And so this is towards the proof of one, show that P and Q are Young tableaus of the same shape. Well, same shape. This is very easy. The number of outgoing lines in each color on the right and on the top is the same. So in each color, same number of outgoing lines, top and right. So the second thing we want to show is that the shape is the shape of a partition. So the thing is done recursively. If we show that the number of red outgoing lines is upper bounded by the number of yellow outgoing lines, and this is good. So let's look at the jump lines. Of the original set, the number of jump lines, and because we are doing a canonical antichain partition, we know this is equal to the height of X. And the number of jump lines of S of X is equal to the height of S of X by the same argument. Okay, now the jump lines of X induce an antichain partition of S of X. So if we look at some jump line of X and we look at all the yellow points on this line, and this is an antichain of yellow points. And so we get an antichain partition with at most as many antichains, and therefore we get that the height of X is at least as large as the height of S of X. So we already know that the numbers are decreasing, and now what we still want to show is that the number of cells in this Young tableau is equal to n. Well, one way to say it is to say, okay, on each height we have exactly one outgoing line. But we can also do it by a simple counting thing. So if a jump line of X contains a element of X, then it contains a minus 1 elements of S of X. Yeah, between two consecutive elements of X on the jump line, we generate one element of the skeleton. And now if we do the sum, then we see that the size of S of X is equal to the size of X minus H of X. And if we do this until we get to the empty set, then we see from this that we indeed have a partition of X. Well, we want to show that P and Q are Young tableaux of the same shape. Now we have settled the shape. The Young tableau definition requires monotonicity in rows and columns. So monotonicity in columns is by definition when we read the heights of the outgoing lines from bottom to top, respectively from left to right, and so we get this. Now, what about monotonicity in rows? So what we want to show here is that the i's outgoing line of S of X is above the i's outgoing line of X. And yeah, maybe we make a little sketch here. So we are talking about an outgoing line of S of X and this outgoing line has a rightmost point of S of X. So this is the rightmost. Now this is the i's outgoing line. And from stuff about canonical antichain decompositions, we know that below this element we have a chain of, so that this is xi minus 1, x1. We have a chain of this length in the skeleton. But now, these points are all generated by some jump line of X. And these jump lines are obviously distinct. And their endpoints are out here. So we find at least I outgoing. And this proves the monotonicity in rows. Good. So we have now seen that if we start with a permutation, and we apply this algorithm, and we end up with two Young tableaux of the same shape. Now we want to show that it's a bijection. So now we have to show that we can get from P and Q to pi. Now, of course, what we are going to produce is the set X, the set of points in the plane, and from this set of points we can read the permutation. And what we show how to go from S of X to X. So then we know how we can get from the set of green points, which is empty in this case, given the tableau, to the blue points. And then from the set of blue points together with the two tableaux to the set of red points, and so forth. So at the end we end up with X. And here is the idea. So I'm again going to give it with an example. So let's see. We know some yellow outgoing lines, and we already got some red points. Say yeah, let's take these. So we have some red points, and we know the yellow outgoing lines, and now we want to generate essentially we want to generate the yellow jump lines. And the way of doing it, wait a second, no, the color is wrong. We got the skeleton, S of X. So it's actually the yellow points, and we want to generate the white points. So a thing we do is here we add a set of marginal points, a chain on the top and a chain on the right. And now what we do, we have this extended set of yellow points. And what we are going to do here is we produce the canonical anti-chain partition of this yellow set of points, but this time we do it backwards. So we start with the maxima. So this means we are going to do jump lines of that kind. jump lines which exit on the left and exit on the bottom and come with, they kind of correspond to going downwards to the third quadrant. Yeah, so we have to start from the top. Oops, wrong. We go out here, and then we take the second one. And out, and then we take the third one. Now we have these jump lines, and the upper corners are occupied by our yellow points, and the lower corners are going to be the points of x. So this is how we get from s of x to x, given the outgoing lines, given outgoing lines, top and right. Yeah. So this shows that we indeed have a bijection. Good. Now let's go to the proofs of the other two statements. So now we want to work with ell-antichains. And yeah, so proof of two. We want to get a maximum ell-antichain A, and this will mean that this is at least as large or equals number of cells in L long this large. S. S is written there. This is the goal, and what's going to be helpful here is that we can define two operations. We have an operation delta, which takes an ell-antichain in X and produces a B, which is a ell-antichain in S of X. And then we have another operation, which is a capital delta, and this is producing, given an ell-antichain in S of X, it's producing again an ell-antichain in X. And the point will be that if B is maximum, then also D is maximum. So if we have this, then what we are going to do is we are going to produce skeleton iteratively until the height of the skeleton is below L. And at this point, it's trivial to have a maximum less equal ell-antichain. Everything will do. And from there, we roll back and produce maximum ell-antichain in S of X. So the first step of this rolling back will be a bit more involved, but besides this, it is easy. So this is what we have to do. And now, so we have an ell-antichain. We take a canonical antichain partition of the union of this, and so we get A1 to, or let's, of X. No. Yeah, so we can take the canonical anti-chain partition. This gives us A1 to AL, and they come with jump lines. A non-crossing set of jump lines, and now we let BI equal to the jump line of AI intersect S of X. And now this delta of A equals P1 to BL. And this is a less equal ell-antichain. I mean, some jump lines of A, if some of these antichains has size 1, then it doesn't generate skeleton point, and we have an empty BI. Okay, and now here is the claim. If the size of antichain is equal to S, then we can conclude that the size of BI is at least S minus 1. Well, let's have a look. We have our AI, and this AI is generating a jump line. This is a canonical antichain partition of the union of A, so it need not be everything. We can have points of X out there which are not covered by a jump line in our collection of jump lines. But we know something. We know that there is jump lines of X, and this point has a jump line of X, and this point has a jump line. No, I shouldn't make it yellow. It's still a white point. And now, if you look at this configuration, and if you recall that the jump lines of X are non-crossing, so either these two jump lines, these two arrows correspond to the same jump line of X, in which case we have here, or even more, points which are on the right jump line, or they are different, but they have to be non-crossing, so one of them has to bend away. And bending away means, so this exists a bend with corner . of AI. And so between any two of AI, we find a bend, which means of the jump lines of X, which means we find a skeleton point. So the number of skeleton points which are on the jump line is at least S minus 1. Good. Now let's go to the second operation, capital delta. So we have a B, which is an ell-antichain. And now what we do is we take the dual canonical antichain partition. Meaning we have the skeleton points, and so this is a BI, and this is a jump line generated by this BI. Well, so this is getting us B1 to BL, and now of course we do the very same thing. We define DI as the jump line. So this is the dual jump line I indicated with, and we intersect it with X. And we have a dual plane if the size of BI is equal to S, and the size of DI is greater or equal to S plus 1. So from this already we define the DIs on the basis of this, and clearly on a jump line you can only have an antichain, so it's again a less equal antichain. But from this statement, if we prove this, then we see that none of the DI can be empty, so it will be an equal antichain. Okay, oops, this is too much. Good. Again, the proof comes with such a nice geometric thing. So we have two consecutive points, and this time what we can say is they are generated by the jump lines. So this is the BI, and here again, in yellow are the jump lines of X. And the jump lines of X, they cover these extremal parts. Okay, and now from a very same type of argument, the jump lines of X are not crossing, and we find a bend of this type. So this means that we find an element of X, and where do we find it? On it. So we find it on each of these, and if you go to the very extreme guys, so where this is outgoing, these are the outgoing. So you find a white point, a point of x left of the first one. You find a point of x below the last one of the bi's. So you get at least as many as bi plus 1. Good. So now we have these two inequalities, and now we want to show what was announced here. If B is maximum, then D is maximum. So claim if this is a maximum, then the size of the delta of B is also maximum. And even more, the size of this delta B equal to size of D plus L. So, for the proof of this claim, we let A be a maximum ell-antichain of X. So we are going to compare the size here with the size of this A. Okay, and now we have the following stuff. We have B, and this is from what we have shown there. Each DI has at least one more. It could probably even have more than one more. So we know that B is upper bounded by the size of delta B plus L. But now this is an ell-antichain in X, and A is a maximum. So this is less equal to A plus L. And now we take the other operator, we take the small delta, and we have seen that this is the size of A and the size of this delta of A. The A can be at most L larger than this one, so sorry, this was the wrong sign. This is on X, this is on S of X, this is a smaller one, minus L. So we get this one, and so this is equal to delta of A. But now we use that B is maximum, and we can put B here. So we have a B at the beginning, a B at the end. We have equality everywhere, and this clearly proves this, and it also proves that the size of delta B and the size of A is the same, and the A was chosen to be a maximum antichain, so the delta B is maximum. Good. So yeah, we have this, and now we have to go to our initialization, we have to see how we really get a maximum ell-antichain of X and what the size is. Yeah, so this is the actual computation of a maximum ell-antichain. So let's look at this diagram again. We are looking for some L, and we find some. No, this is more the one that we want to look at. So we find a K, so that where we are leaving this Ferris shape. So there is a K such that the height of the K times iterated skeleton, I'm omitting the X here, is equal to H, and this is at least as large as L. And then if we go one further, and we look at the size of the K plus first iterated skeleton, then this is R and this is less than L. So this is the critical situation. Here we are, if we got for this K maximum ell-antichain, then using the stuff that we have there, the operator delta, capital delta, we can go back and to gain L everywhere. So we get this size added when we arrive here. The problem is to get the initial guy. Okay, now given this, we know that all of sk minus plus 1 is a less than L antichain. And actually it's an R antichain. And now if we look at this, is a maximum R antichain in S of K, S to the K. And we also know that the size of this is the size of Sk minus 1 is the number of cells here. The size of this one is we add R here. So the stuff that's missing is this L minus R. This is R here, and this is H. Okay, so the size of this is equal to the size of Sk plus 1 plus R. Now, we look at a maximum chain in SK. And well, we know the size of this maximum chain is H, and it's at least as large as L. And well, the size of the intersection of C with this is at most R, because well, this is an R antichain, and a chain can intersect an R antichain nothing more than this number of elements. Okay, now let's do another line of computation. Let's look at the size of SK. So this is at least as large as the size of C union SK delta SK minus 1. Delta SK plus 1. And now, again, this is equal to the size of C plus the size of this one minus the size of the intersection. So we know these values respectively. We know about in the last one. So because we are going to subtract, we are getting this. This was an H. This is the size of SK plus 1 plus R. And the last one is a minus R. This is the upper bound on this. So it is equal to SK plus 1 plus H. But this is equal to the size of SK. By looking at the shape of our partition, we know the last one here. So we start with SK, we end with SK, and we conclude that SK minus delta SK plus 1 is a subset of the chain. So we cover everything but a chain with this maximum R antichain. So from this geometry, we have this delta SK plus 1 is an R, and then we have the rest of this is a C, and we get a maximum ell-antichain of SK by adding any L minus R elements from this set that we already addressed. So C minus delta SK plus 1. Yeah, so now we have a maximum ell-antichain. Its size is equal to the number of cells covered by this part of the Ferrous shape. And now with the capital delta operation, we can go back and we add another, no, twice. It should be, so we got this one in the first place, and now we're adding another L in each step. And finally, we arrive at an ell-antichain in X which has the given size and is maximum. Good. So this was the proof of 2, and now we come to the proof of. So we are heading for a maximum K-chain, and this time we're going to show that the number of elements covered will be at least as large as the number of cells in longest K rows. But from the orthogonality of this pairs AC, it is clear that this greater equal has to be an equality. But our proof will give the inequality. Okay, so let's look at an arbitrary chain family. Arbitrary chain family, this is a set of elements which can be covered by a certain number of chains. And now what we do this time is we take the canonical chain decomposition with jump lines of this form. So right outgoing, bottom outgoing. And clearly we have to go from this side. So the first one here would probably be this one. Not probably, it will exactly be this one. And the next is this. And then we have this and maybe this. So what we get here from this canonical chain decomposition, we get a partition of the plane into regions. And we are going to count these regions R1, R2, R3, and so on. So a region is the area which is between two consecutive jump lines of this canonical chain decomposition. And yeah, the idea or the construction of our maximum K-chain will be very easy. Assume that you have a family C prime, which is a maximum K-1 chain in the skeleton of X. Now, the maximum K-1 chain comes with C1 prime to CK-1 prime, the canonical chain decomposition, and this comes with jump lines and this comes with regions. And so we have K-1 jump lines, we will get K regions, R1 and RK. And now the thing is very easy. Let Ci be maximum chain when X intersect Ri. So we extract a chain in this region, and now the claim is that the family C1 to Ck that we obtain is a maximum K chain in X. So from a maximum K minus 1 chain in S of X, we get a maximum chain in K chain in X. So this time the algorithm is really, the computation is very easy. We iterate down until we get to S to the K. Then we take a single maximum chain, and then we have two regions for the skeleton bond level higher or lower rather, and we iterate down until we get a maximum K chain. So we just have to prove this claim. Yeah, and how is it done? Yes, so now we have to be slightly more careful about the definition of the region, and the way I'm going to think of a region. Let me just draw a part of such a region. So we are going to correct, from the way we did it. This will be the jump lines of the maximum K minus 1 chain in S of X. So these are the points in S of X. And now what we do for the definition of the regions, we kind of change the boundary slightly. So we go on such a curve which is slightly above the jump line. And now when we look at an antichain of X, so a antichain of X, then we get a jump line of A, and of course we are doing it, well, this time we are doing it the standard way, so this will be the point in A, and this will be our jump line. And A is crossing R, this is our region R, crossing R well, if and only if the picture is like this. So what do I mean with this picture? So the left entry is vertical and the right exit is horizontal. And to emphasize entry and exit, let me draw these two arrows. This is the entry arrow, it's vertical, and this is the exit arrow, it's horizontal. This is the definition of crossing well. And yeah, so let's put some examples. So what you see is the only one which is crossing well is this one. This is well. Here we fail at the entry. Here we fail at the entry. Here we fail at the exit. And maybe we change this slightly. I mean, interesting case is also if some of the yellow guys of the skeleton points are incorporated in the jump line. So this is leaving well but entering wrong. So it's not crossing well. Okay, so this is a definition of well crossing. And now if we look at the canonical antichain partition of X, and we look at the size of Ci. So here, up there is the definition of Ci. It's the maximum chain in X intersect Ri. So what can we say about the size of Ci? We claim that it's at least as large as the number of Aj. These are the canonical antichains which cross Ri well. Yeah, if you are crossing well, then there is a point. And the antichains in this region, if you have several points and several well crossing jump lines, then because one jump line is completely dominating the other one, they form a chain. So this is why every well-crossing antichain contributes 1 point to the height in this region. And we get a chain which has this size. Yeah. Given this, we are close to the end. So now the size of the chain, the number of elements covered by the chain family equal to the sum of the sizes of the Ci is at least as large by what we just saw, the number of well-crossing pairs Aj Ri, and now we can in principle change the order of summation, and to do so we need some lemma. So here is a lemma. If A, an antichain from the canonical antichain partition of x if the jump line of A intersects C prime in M points, then it follows that the jump line of A is well crossing at least M+1 regions. Yeah, and for the proof, I'm again going to give you a picture. So this is an antichain from the canonical antichain partition. So I can go with the usual color, and now here we have the skeleton points. And we have the boundaries of the regions. Okay. And sorry, this is not exactly what I wanted to draw. We have maybe many regions and few intersections. Okay, so now these two are the two guys which give us m equals 2. And now we have to verify that we have at least m+1 regions which are crossed well. And the idea is to say, okay, we go starting from this point. Here we enter in a good way, and we write a 0. Here we cross horizontally, it's a 1. Here we cross vertically, it's a 0. Horizontally, 1. Here we leave horizontally 1. Here we arrive horizontally 1. So between these 2 points, we see a sequence of zeros and ones. And the claim is that for every consecutive pair, 0, 1, we have a well-crossed region. And the important thing is that we know that the first entry is a 0 and the last entry in this string is a 1. So there has to be a change of sign in between. And yeah, in this case, we would get these 2 points in these 2 regions which are well crossed. We actually even have a point here in this region, but we don't count it. Yes, and then we have to adapt the definition of well crossed for the 2 outer regions, for the regions which have only one boundary, but clearly this one is well crossed, and this one is also well crossed. So it's the outer one is well crossed if the entry is good, the lower one and the upper one if the exit is good. And in total, we get at least m+1 regions which are crossed well. Because we get one before the first point that we count here, one in between every two, and one after the last one. Okay, now let's go for a second lemma. Yeah, so the prime K minus 1 chain in S of x, then we claim that the construction yields a K chain in X of size at least of size at least the size of C prime plus H. This is the height of X, so this is the maximum that we can expect. And yeah, the proof is the thing that we already started with up there. We look at the size of C, and this is equal to the sum of the Ci, and this is upper bounded by the number of well-crossing pairs, A, J, R, I. And now the lemma allows us to take advantage of a change of summation. So now we sum over the antichains, and we have the number of Ri crossed well by Aj. But now from the lemma that we just have, so this is the lemma. This is at least as large as the. I'm writing it differently. The number of skeleton points on AI plus 1. Skeleton points intersect with C prime plus 1. But now, since the AI is a canonical antichain partition, the union of these sets of skeleton points of the different antichains is all the skeleton. So in total, we get all the elements of C, and every antichain is adding 1. So this is actually equal to the size of C prime plus H. And this is the claim. Yeah. And this is the best we can expect. So if you look back to the Ferris diagram, then you go to SK, and then there you take the maximum chain, and you get this pile of cells, and then going back, you always add the height of the respective skeleton, so when you come back, you have exactly this size. But all this is, in each step we have a lower bound, so you have at least this number of cells. And this tells you that, by going into the orthogonal pair, we immediately obtain that this has to be equalities and this is maximum. So we have a nice algorithm for computing these maximum chains for all maximum K chains. Yeah, so seems that this was again a quite long lecture, but we did everything with details and proofs. I'm quite happy. I think it's a beautiful result. Thank you.